revelation, of the death of this man on the left. Obviously you recognize Einstein. This man is Georges Lemaître, who is the father of the Big Bang Theory. Science and religion, conflict? Hang on. Catholic priest, greatest cosmologist of the modern era. In 1927, he solved Einstein's equations of general relativity, Einstein's theory of gravity for the universe as a whole. He came up with an expanding universe solution. And in 1931, he came up with a further solution in which the universe expanded from an initial compact, dense, tiny state. And he called that the primeval atom. It was later dubbed the Big Bang by a Cambridge cosmologist called Fred Hoyle, who I'll come to, who actually didn't really like the idea and proposed an alternative in which the universe was eternal. But the Big Bang won the day. And so it was predicted by Einstein, and it is now extremely well supported by evidence. The expansion was one piece of evidence. That wasn't enough for Hoyle and his colleagues in Cambridge. They said, well, okay, we can explain this expansion, the matter pulling apart, space expanding and pulling apart, by saying that new matter comes into existence in the space that's left by the galaxies as they retreat. And if it comes into existence at just the right rate, then we can have an eternal, unchanging universe. The clinching evidence was the cosmic background radiation that was discovered in 1965 by these characters, Penzias and Wilson. They had what they thought was bird droppings in their antenna. It turned out to be the remnant radiation from the origin of the universe. They had to be told what it was by cosmologists, but they got the Nobel Prize. But it was terrific. It had been predicted on the basis of the Big Bang in about 1948. But there was this rivalry between the Big Bang and the steady state until this point, because the steady state couldn't explain it. On the basis of the Big Bang, at very early times, the universe would have been much hotter, and it would have cooled as it expanded and left this radiation behind. Okay, and just to give you a flavour of what we're talking about in cosmology, that's a typical galaxy. There are something like 100 billion galaxies in the observable universe, each with 100 billion stars. In fact, that number keeps going up, probably by a factor of 10 or so. So that gives you some idea of the scale. And the universe started some 13.8 billion years ago in this fireball we now call the Big Bang. That's an important part of the story, because what happens is that as the universe expands, galaxies and stars form by gravitational contraction. The earliest stars, which are large and blow up eventually as supernovae. They run out of the nuclear fuel that's keeping them going, and the Big Bang just bequeaths us hydrogen and some helium, but all the other chemical elements of which you and I and our planet is made are built inside stars by nuclear fusion, by nuclear reactions, and when these stars explode as supernovae, they make available that material for subsequent generations of stars to become planets. Now, the Big Bang, it seems to me, poses potentially two questions that may or may not relate to theology. One is that the universe began to exist, seemingly 13.8 billion years ago, and the other is that it is fine-tuned for life, apparently. In fact, yesterday at the Royal Astronomical Society meeting, I was at the specialist discussion meeting on this fine-tuning of the universe. This is something that's come straight out of cosmology, and there's a live point of discussion in cosmology, the special way in which the universe has been set up. And in the latter part of the day, there's a lecture by a colleague of mine with whom I've written a book about Lemaître, on Lemaître, to commemorate the 50th anniversary of his death. So all I'm talking about today is absolutely live, up to date. This is happening in the cosmological community, these sorts of debates and discussions. Well, it's interesting to think about what theologians have said in the past. Interestingly, Stephen Hawking quotes Augustine, who said that assuredly the world was made not in time but simultaneously with time. It's rather interesting that back in 400 AD, a Christian theologian, on the basis of his theology of creation, would say that time, space and matter came into existence together, which is essentially what the Big Bang theory is saying. But of course, Augustine couldn't know any of the detail that we have today. Now, as I said, Fred Hoyle didn't like this idea of the Big Bang. Stephen Hawking doesn't like the idea that the universe had a beginning either. And he has proposed something he calls the no boundary proposal, which he thinks gets round the idea of the beginning, because he says this: so long as the universe had a beginning, we could suppose that it had a creator. But if the universe is really completely self-contained, having no boundary or edge, then what it would not have neither beginning nor end. It would simply be, what place then for a creator? Well, of course, Hawking has a very deistic view of the creator. This is the only role he can conceive for the creator, namely to light the blue touch paper at the beginning and set the universe going, which is certainly not the way Christians see God as creator. But nevertheless, let's pursue this for a moment. He said that back in A Brief History of Time, and in his more recent book, The Grand Design, he says the same thing. There are actually serious philosophical and scientific problems with his no boundary proposal. I mean, it's very ingenious and sophisticated mathematically, but what he says is that as you track back the history of the universe, time becomes imaginary. It becomes like another space dimension. I mean, it's imaginary in a technical mathematical sense of imaginary numbers. And that's really highly problematic. The curious thing is, he only says that in his popular books. If you read his technical articles, there is nothing about getting round the idea of the origin of the universe and it having no beginning. It does begin in his technical articles, because it begins from the place where this four-dimensional space you start from merges with the three dimensions of space and one at a time that we know. But he has this kind of polemic. It's very interesting that the current state of play in cosmology, it looks like the universe really does have a beginning. Back in, this is a guy called Alexander Vilenkin, a cosmological colleague of Hawking, who there was a symposium in Cambridge back in 2012 to celebrate Hawking's 70th birthday. Sadly, Hawking couldn't be there. He was ill in hospital, as he periodically is. I mean, goodness me, it's another 4 years on. It's utterly remarkable that he's still alive and going strong today. But he sent a message to the symposium along the lines I've just said. Well, if the universe had a beginning, then it would need a creator. But this man, Alexander Vilenkin, has proved certain so-called singularity theorems, and he announced to the conference that all the evidence we have says that the universe had a beginning. If you kind of backtrack a light ray going back to the beginning of the universe, then it actually does come to a beginning. This is the kind of gist of what Vilenkin has said. However, let's go back to theology again. Here is St. Thomas Aquinas, and he had this to say. He said, basically, by faith alone do we hold, and by no demonstration can it be proved that the world did not always exist. So, this was a matter of faith for him. Cosmologists today seem to have theorems which show that it does begin to exist. But nevertheless, for Aquinas, the point is that even if the universe didn't have a beginning in time, it would still need God to create it. If the universe goes back infinitely far in time, we have the whole sequence of cause and effect. That sequence would still need God to create it. The universe still needs God, and I'll come back to that point in a minute. But here's another piece of fun. This is a guy called Lawrence Krauss, who a few years ago wrote a book called A Universe from Nothing. Lawrence Krauss thinks that the universe creates itself from nothing. And if that sounds paradoxical to you, it's paradoxical. The thing is, he redefines nothing to be a rather sophisticated and complex something. Namely, something that's called the quantum vacuum. And vacuum doesn't mean just empty space anymore. The vacuum in quantum theory is complex, with particles coming into existence and annihilating in a split second and so on. It's a hive of activity. And I think that Krauss, and Hawking says similar things too, makes a mistake rather similar to this one that happens in Through the Looking Glass, in which the conversation gets more and more confused as it goes on. I see nobody on the road, said Alice. I only wish I had eyes, the king remarked in a fretful tone, to be able to see nobody, and at that distance too. Who did you pass on the road, the king went on, holding out his hand to the messenger. Nobody, said the messenger. Right, said the king. This young lady saw him too. So, of course, nobody walked slower than you. I do my best, the messenger said in a sullen tone. I'm sure nobody walks much faster than I do. He can't do that, said the king, or else he'd have been here first. Now, this is very entertaining. But you see, I think that the confusion here is between nobody in the sense of the absence of anybody, any person at all, and a Mr. Nobody with a capital N. And I think people like Krauss, who say that the universe creates itself out of nothing, are confusing, making a similar kind of confusion with nothing. Nothing that is the absolute absence of anything at all, and nothing which is a rather sophisticated something. Yeah. You saw that, did you? I hope you saw that. You saw that. But anyway, I was reading it through. Okay. Now, getting back to Aquinas again and some more theological thinking, the real question to which the doctrine of creation provides an answer is not why there is a temporal beginning, but it is why there is anything at all. And the reason God provides that is because God is necessary, and the universe is what the philosophers call contingent. At least part of what we mean by the very concept of God is that he exists necessarily. That is, he cannot not exist. There never was when God was not. And so the naive Dawkins question, well, who created God then, is actually a misunderstanding. Because anything that's created is not God. So you can argue about whether a necessary being exists, but if he does, then there never was when he was not, and is not created. But on the other hand, the universe is contingent, and lots of features about the universe are contingent. It may or may not have existed, and it could be different from what it is. And this is the general philosophical view of things. It didn't have to exist in the way that God does. So the interesting thing there is that Stephen Hawking himself recognized this very point when he wrote this back in A Brief History of Time. What is it that breathes fire into the equations and makes a universe for them to describe? Precisely. We were talking yesterday at the Royal Astronomical Society about ultimate theories, theories of everything, better physical theories than we've got now, and there's the search on for this kind of theory. It might be Hawking's favoured M theory, which I'll come back to in a minute. But anyway, the point is, we might have the most beautiful theory, but why is there a universe to which that theory applies? Okay, so that's really the first part of the talk I wanted to give, to do with the why there is a universe type of question, and whether or not it had a temporal beginning. Now, the second is to do with the specialness, the so-called fine-tuning of the universe, which relates to two kinds of things: initial conditions and the physical constants. And as I say, this is live. There's a whole day's special discussion at the Royal Astronomical Society about these issues. Space or time doesn't give me the opportunity to say, give you many examples, but yesterday we had example after example after example. The first talk by another friend and colleague of mine, Bernard Carr, who's written a book and indeed contributed to the Lemaître volume I was talking about. He gave numerous examples of so-called coincidences about how these physical constants, for example, relate together. The physical constants are things like the strengths of the fundamental forces of nature, the masses of the fundamental particles, that sort of thing. So, a couple of examples. Okay. Right back near the beginning, 1 second after the origin of the Big Bang, the mean density of stuff, of matter, energy in the universe needed to be what it was to 1 part in 10 to the power 15, one with 15 noughts after it. Okay? Very, very high degree of accuracy. In fact, the universe is sitting on a knife edge between expanding forever and ultimately recontracting. If the mean density of stuff is slightly more than this critical value, then gravity will pull back the universe, and if it's greater than the critical value by more than this tiny amount, then it'll be pulled back very fast, and there will be no time for anything interesting to happen. On the other hand, if the universe the mean density of stuff is less than this critical value, then the universe will expand forever, and indeed, if it's less by more than this tiny amount, then the universe will expand far too quickly for anything interesting to happen, for galaxies and stars to condense out of the expanding gas. So that's one example. Then relating to the initial conditions, and then here is another example which is particularly interesting. This relates to how the elements are built up inside stars, which I was referring to earlier: carbon, nitrogen, oxygen, the elements we need for life, made inside stars. And you need an extraordinary kind of set of coincidences in order to be able to make carbon in the first place. You do it by crashing 3 helium nuclei together, and it's very difficult because the intermediate element, beryllium, is only around for a tiny fraction of a second. It needs a special effect to make that reaction go, and then you need to make oxygen, you need to crash another helium nucleus on, and you don't need to destroy all the carbon in the process. And this depends all very critically on the strong nuclear force, the force that holds atomic nuclei together. The really interesting thing about this is that it was discovered by none other. This coincidence was discovered by none other than our atheist friend, Sir Fred Hoyle, the Cambridge astrophysicist who was a proponent of the steady state theory, and he made broadcasts on the BBC in the late 40s and 50s, saying things like religion is an illusion. Anyway, when he made this discovery, he said that a super intellect was naked with physics and with all of biology, and there are no blind forces in nature worth speaking about. Nature, it's a put-up job. Otherwise, you're just left with a monstrous sequence of accidents, he said, which he wasn't prepared to accept. So he started talking about a super intellect. Couldn't quite bring himself to use the term God, but a great mind behind the universe. I mean, what are we talking about here? It's semantics, I think. Now, there's some discussion, of course, about whether this fine-tuning is real and so on. But I think most cosmologists, and certainly yesterday, think it is. There's some argument, certainly Paul Davies, whom I've had the privilege of debating with, says that like the porridge and the tale of Goldilocks and the three bears, the universe seems to be just right for life in so many intriguing ways. It's a mystery. But now, how might we explain it? Well, if we believe in God, then there's a sort of natural explanation that, well, God intended the universe to bring forth stars and planets and life, intelligent life, so that creatures would be able to have a relationship with Him. It's interesting to see what strategies are available if you don't want to go down that route. And there are two. Again, these were discussed yesterday at the Royal Astronomical Society. The first is to seek an explanation from within science, to find the ultimate theory of everything, and to say, well, actually, we may get this ultimate theory which calculates all these constants, these different things which I've treated as parameters that you just have to put into the theory, and you get by observation. Well, we may get some theory, some ultimate theory, which calculates them all. So they can't actually take values different from what they do. They have to take these values, so you kind of have to lump it. This is the only sort of viable set of, if you're going to have a universe, it has to be this universe. I mean, Einstein once asked, did God have any choice in making the universe? The answer would be essentially no. But then, then the alternative is the diametric opposite to that. And this is really the front runner at the moment. My friend Bernard Carr says that basically, if you want to avoid God, then you have to opt for a multiverse. And this is a gigantic collection of universes, and it's often rather blandly put that if every kind, in other universes, all the values of the constants that they can take are instantiated in this gigantic collection of universes, usually taken to be infinite, then we shouldn't be surprised that we're in this particular universe, because there are all these other ones, but this is the one that's just right for us to be here. But it only exists because the whole multiverse exists. But there are puzzles for each of these strategies. So if there's only one set of laws or one set of constants, then I think we are left with a deep puzzle as to why it's that particular set of laws which applies to the universe, which is maybe the only has this unique set of physical constants. And it looks as though there can be other laws with other kinds of constants, but suppose there were only even one set of laws. Well, that would be deeply puzzling, because we can imagine universes that are lifeless, maybe just a few particles floating free in otherwise empty space. We can certainly imagine universes which don't produce intelligent life, and it's very puzzling that this one happens to, even if the constants have to take the values they do so. And then for the multiverse strategy, well, there are lots of different ways of getting multiverses, even lots of different ways of getting infinitely many universes. And so basically what happens, actually with either of these strategies really, is that the question gets pushed up a level. So it goes from, okay, why is this universe fine-tuned, to, well, why is the multiverse fine-tuned so that some members of the multiverse give rise to life? Because that is by no means guaranteed merely by adopting a multiverse. And and if we do find the ultimate theory of everything, which derives all the constants, then again you can say it's just been pushed up a little. Why is it that particular set of laws which gives rise to those constants that are just right for life applies to this universe? So it seems to me that this question never really goes away. Okay. A few recent developments in cosmology. Now, this is a guy called Alan Guth who's come up with a theory called inflation, and what it involves is a rapid period of expansion. You've got time on this axis, and very early on, the universe, in the first 10 to the minus 32 seconds, the universe expands vastly, at an enormous rate. And what this does is drive some of the parameters to the right values, so particularly that density parameter that I was talking about. But from the fine-tuning point of view, inflation itself, it turns out that inflation itself needs fine-tuning. So you've sort of just shifted the problem up a level. In cosmology, they've rather alternated between these two different strategies, if you like, because the turn now is to a multiverse version of inflation, and that's what these sort of chaotic and eternal inflation ideas are. That we might have an infinite space in which some regions inflate, others don't, and within inflating regions you get other bubble universes coming up, and so on. Now, there's one more thing to mention on recent developments. Particularly this is important because it's called string theory. This is Leonard Susskind, one of the pioneers. You don't need to understand what it is. I mean, it's incredibly complex and technical, but basically matter isn't point particles anymore, but tiny vibrating strings. Now, this was meant to be the candidate theory of everything. It was meant to predict the masses of the particles and the strengths of the forces and so on. This was the original motivation for string theory. After 40 odd years or so, it hasn't actually made any predictions. So Susskind and colleagues have moved to what they call the landscape of string theory, which is a multiverse version of string theory, in which maybe there are 10 to the 500 different solutions of the theory, which are all supposed to be instantiated in different universes. This is, I mean, Hawking favours this theory. M theory is a generalised form of string theory, and that's the theory that Hawking himself now is really opting for. But the idea is that if you have all these number of solutions, then of course it may or may not be enough, and that's a sort of significant issue, even then, to cover all the possibilities, and so that's still an issue. But be as it may, the idea is then, well, we shouldn't be surprised to be in this universe because it's one of this collection, and it's our one that's right for life, whereas most of the others aren't. Now, there are lots of other theories out there. The Big Bang paradigm is kind of is secure, really. I mean, very well supported by evidence. But the sort of things that happen in the first 10 to the minus 32 or even earlier are really highly kind of controversial, contentious, speculative. So this is a Russian physicist called Lev Landau, who said, cosmologists are often in error but seldom in doubt, which I think is rather fun. Now, somebody has to be wrong at the moment, because there are there's a lot of really very fine observation going on. I heard a talk yesterday about recalibrating the distance scale to the stars and the galaxies and so on. Extremely fine work being done in Cambridge on that. But there's brilliant work being done at that level. But there's a lot going on the theoretical side too. But it's rather outstripping the observations. Okay, so I think, and I'll just kind of whiz through these. That, I mean, this multiverse idea, my friend Bernard Carr says, basically you have to go for this idea if you want to avoid the need for God, but it is fraught with problems. The physics is, as I'm saying, is highly speculative. We need some theory which combines quantum theory, the theory of the very small, with Einstein's theory of gravity, because that's what you need in the very, very early universe. 10 to the minus 43 seconds from the origin. Which you 1 divided by 1 with 43 noughts after that fraction. So we need a theory, and string theory, stroke M theory is a candidate, but it's not the only one, and it's, as I say, it's not made any predictions, highly speculative. There's a problem about infinities, infinitely many universes. There are various paradoxes to do with infinity. Mathematicians, happily deal with different degrees of infinity. Although, having said that, I think Cantor, who produced the arithmetic of this, did go mad at the end of his life. But mathematicians play with infinities. In the physical world, real infinities do cause certain paradoxes and problems. And of course, you can always add to an infinity. You might, here are infinitely many numbers, 1, 3, 5, 7, 9. But that set of numbers doesn't have the property of evenness. So even if you have infinitely many universes, you're not guaranteeing that any will have life. There's a sort of paradox about human identity. As soon as you go down this route, if anything, however small a probability for anything arising it will arise in an infinite unit multiverse infinitely many times. So there'll be replications of this room. There'll be replications in which, I had a late night last night and decided I wouldn't bother to get up this morning and come and give the lecture. This doesn't disprove the idea, but if there's a simpler way of thinking about it, if there's a simpler hypothesis, that brings me to this very point. There's a principle of Occam's razor. You take the minimum number of entities needed to satisfy the data in a scientific theory if you've got competing scientific hypotheses. And this one doesn't seem to be simple for that kind of reason. You hear this sort of mantra that anything that can happen does happen somewhere in some time in some universe. And that sort of is a bit of a recipe for extremely puzzling and odd things happening, and actually a demotivation to do real science. We sometimes talk about a God of the gaps, where God is introduced to fill gaps in the explanatory scheme of things. Say in biology, life's too complicated to get going. There's this intelligent design movement, for example, the eye is too complicated to arise. So we've introduced a God of the gaps. God stepped in at that point. Well, there's a bit of an idea of a multiverse of the gaps here. We might get some puzzling feature in our lab, and not pursue what I call normal science, but we could be tempted to explain on the basis, well, we're in a multiverse. It'll happen somewhere, sometime, in some universe. There's a big problem in cosmology with something called the cosmological constant. Perhaps the biggest mismatch between evidence and observation in cosmology. This was talked about yesterday. Einstein had this so-called cosmological constant in his original equations, and then later on called it his biggest blunder. It looked like it was zero. Lemaître did have a value of the cosmological constant in, and it's recently been shown that the universe is accelerating. What this cosmological constant does, it's kind of like an anti-gravity, and it pulls the universe apart faster, so the universe is accelerating. So it looks like it takes a small positive value. But when physicists calculate what they think it ought to be, they get a value that's 10 to the power 120 times too big. So this constant seems highly, highly tuned. To get, some fine-tuning seems to be needed anyway with a multiverse. To get a multiverse in the first place, what would the right kind of multiverse? Many of the kind of multiverses that I'm talking about actually consist of they're a single universe, an infinite space, but with lots of different regions which don't interact, and you can't get signals from other universes, so you can never observe them. But to get an infinite overall space, you need the density parameter that I was talking about for the whole cosmos, that whole infinite space, to be less than critical value. So that's a degree of fine-tuning. And if it were greater than that, then the universe would actually be finite in size. Then there's a question about the amount of order in the universe. It looks... What the multiverse does, essentially, is explain why there are observers in the universe, why there are creatures like us able to observe it. But being able to observe the universe doesn't require the degree of complexity and order and structure that we actually see. In order for kind of normal calculations of probability to make sense in our universe, we need to regard ourselves as typical observers. So, but in a sense, we're not. A typical observer would be much more like an observer that's in a world that in which there's a single solar system surrounded by utter chaos and junk, not the 100 billion galaxies worth of order that we see. So I think this is a serious problem for multiverses. It looks like it's ultra fine-tuned in some ways, so that we live on a large planet. We are able to interact with each other. We're able to do science, and there are a lot of extra conditions that are needed, or an extra fine-tuning that's needed to allow that to happen, which takes you beyond what you'd expect if this universe were a typical member of the very small, albeit subset of universes that were life-bearing. So the theistic explanation, it provides an ultimate explanation. It explains why there should be life, because God had purposes and intentions for there to be life, and God freely chose to create this particular universe, intending that it produce intelligent creatures. Of course, he could have created through a multiverse and provided the right kind of multiverse. It doesn't by no means rules out God, although, as I've said, I'm certainly a multiverse skeptic for the kind of reasons I've been saying. And God explains why the universe might be as ordered as it is. Back to George Lemaître, 50th anniversary of his death this year, back in June. He made this, I think, very interesting remark. There were two ways of arriving at the truth, and I decided to follow them both, which I think is, well, I can identify totally with that. Science and theology. So I'll stop at that point.